Okay, today we study about group automorphism. So, what is the definition of automorphism? A map A from G to G, where G is a group, where G, comma, composition is a group, is said to automorphism if F is 1 1 onto and homomorphism. That is a preserved group operation. That is it preserved group operation. So that is F of A B, A composition B, that is equal to F A composition F of B for all A B belongs to the group G. If G থেকে G, F is a mapping which is 1 1 onto and preserved group operation. So F of A composition B, that is equal to Fa composition F of B. Then if we say that F is an automorphism. If F is 1 1 onto and homomorphism, that is F of A composition B equal to Fa composition FB, then the mapping A from G to G is said to be an automorphism. So now we give some examples of automorphism. We consider the group C, comma, plus, where C denotes the set of all complex numbers and plus is complex addition. Define phi from C plus to C plus by phi of A plus IB, which maps to its conjugate A minus IB. Now we check that F is an phi is an automorphism. So first we check the 1 1 property. Let phi of Z1 equal to phi of Z2. That is Z1 equal to say A1 plus IB1 and Z2 equal to A2 plus IB2. By definition of phi, this the image is A1 minus I of B1 and A2 minus I B2. So which implies that A1 equal to A2 and B1 equal to B2. So this implies that A1 plus I of B1 equal to A2 plus I B2. So this implies that Z1 equal to Z2. Conversely, we get if Z1 equal to Z2, then this happen. conversely we get the this. So phi is 1 1 and well defined. We say this 1. Now we say that phi is onto. So let z equal to a plus ib be any arbitrary element of C, and take z dash equal to a minus ib, which is also a complex number. Then phi of z dash equal to phi of a minus ib. This is equal to a plus ib equal to z. So this implies that phi is onto. We write this as 2. Next we show that phi is homomorphism. So for that, let phi of z1 plus z2, this is equal to phi of z1 means a1 plus ib1, and z2 means a2 plus I of b2. So this is, I write real part we take as same side and complex part we take in another side. And by definition of phi, we write this as a1 plus a2 minus I b1 plus b2. So this is equal to a1 minus I b1 plus a2 minus I of b2. So this is equal to phi of a1 plus ib1 plus phi of a2 plus I of b2. That is equal to phi of z1 plus phi of z2. So we show that phi of z1 plus z2 equal to phi z1 plus phi z2. So phi is a homomorphism. So from 1, 2 and 3 implies that phi is an automorphism. Phi is an automorphism. Example 2, if we take phi from set of all complex number star comma dot goes to C star comma dot, where C star equal to C minus of 0, and dot means complex multiplication. Dot means complex multiplication. So if we take phi of a plus ib, this goes to a minus ib, then we can check that phi is also an automorphism on the group C star comma dot. So phi is also an automorphism. Next example, we take phi from R2 to R2 by defined by phi of AB. This goes to PA, where R2 comma plus is a group. So we check that phi is also an automorphism. So for that, first we prove phi is 1 1 and well defined. Let phi of a1 b1 equal to phi of a2 b2. This implies that by definition of phi, this is b1 a1 and this is b2 a2, which implies that b1 equal to b2 and a1 equal to a2. So this implies that a1 b1, this pair is equal to a2 b2. Conversely, we get this. So we say that phi is well defined and 1 1. Now we prove phi is onto. For that, let x equal to ab belongs to R2 be any arbitrary element. Be any arbitrary element of R2. Take y equal to ba. This is also element of R2 such that phi of y equal to phi of b of a. This is equal to ab equal to x. So this implies that phi is onto. Next we prove that homomorphism part. For that, let 2 point x1 equal to a1 b1 and x2 equal to a2 b2. So phi of x1 plus x2, this is equal to phi of a1 plus a2 comma b1 plus b2. This pair is mapped to the point b1 b2 a1 plus a2. This is equal to b1 a1 plus b2 a2, that is equal to phi of a1 b1 plus phi of a2 b2, that is equal to phi of x1 plus phi of x2. So phi is an homomorphism. So from 1, 2 and 3 we say that phi is an automorphism on R2. So geometrically this phi reflects each point in the plane across the line y equal to x. So reflection about any line passing through origin is an automorphism of R2, as well as any rotation about origin is also an automorphism on R2. Next is defined what is inner automorphism. Inner automorphism. So for any element A of the group G, the function phi of A from G to G be defined by phi of A of x, this mapping to A x A inverse for all x belongs to the group G. This phi of A is called inner automorphism. Is called inner automorphism. Inner automorphism of G of the group G induced by A. Induced by the element A. Now we give an example of an inner automorphism. We take the group ASL2R, that is all matrices of 2 by 2 matrices with determinant of A equal to 1. All 2 by 2 real matrices with determinant equal to 1. If we take phi from SL to R goes to SL to R and take a element, say M belongs to SL to R, and phi of M is defined by phi of M of A. This maps to M inverse. Then we can check that phi of M is an automorphism. So for that, first we check phi of M is 1 1. So phi of M of A equal to phi M of B. By definition, this is equal to M inverse, and this is equal to M inverse, which implies that A equal to B. First of all, we take M inverse. By this, M is cancelled out. After that, M we get, also M is cancelled out, we get A equal to B. If A equal to B, then this hold, and this is phi of A equal to phi B. So phi of M is 1 1. To check on to, let A belongs to SL2R be any arbitrary element. If B belongs to SL2R such that phi of MB equal to A, so this implies that MB M inverse equal to A. So B equal to, we get M inverse of A M, and also determinant of M inverse A M equal to det of M inverse, determinant of A, determinant of M. So this is equal to determinant of A equal to 1, determinant of M inverse M, that is equal to determinant of identity determinant is 1. So this is 1. So for any A, there exists a matrix B such that phi of MBA equal to A. So phi is onto. Next we check homomorphism. So phi of M AB, that is equal to M of AB M inverse. So here we introduce M inverse, and M of B m inverse. So this is equal to phi m of A into phi m of B. So phi is homomorphism. So phi of m is an automorphism. This type of automorphism we known as inner automorphism of the group SL2 are induced by the element m. This is automorphism. Next we show that the set of all automorphism, that is odd G, odd of G denote the collection of all automorphisms phi from G to G. This collection is we called odd G, and in of G is denote the collection of all inner automorphism phi of A, such that A belongs to G, where phi of A is defined by phi of Ax equal to Ax inverse for all x belongs to G. So collection of all inner automorphism we denote by in G. So we first theorem is we show that the collection of all automorphism, that is odd G, and the collection of all inner automorphism, that is in of G, are groups with respect to function composition, are groups with respect to function composition. So we know that if S is any set, take S is any set and A of S is collection of all function from S to S such that F is 1 1 on 2, that is collection of all bijective mappings from S to S. We can check that AS is a group with respect to function composition, with respect to function composition. So first, if we take FRG to elements of AS, to bijective mapping, then the composition of two bijective mapping is also bijective, so closure property is satisfied. Second condition is associative property. We know that the matrix function composition satisfies associative property, that is F composition H composition G, that is equal to F composition H composition G. And third is identity mapping, I of x equal to x for all x belongs to S. I is identity mapping is the identity element of this group for all F in A of S. So identity element exists. Next we check inverse. For any F belongs to AS, F inverse is also in S. We know that the inverse of a bisective mapping is also bisective, and F composition F inverse equal to F inverse composition F equal to I. So AS, that is collection of all bijective mapping from S to S, is a group with respect to function composition. So now to show odd of G, that is collection of all automorphism from G to G, is a group, we will show that a odd of G is a subgroup of AG. This is a symbol of subgroup, is a subgroup of AG, where AG is the collection of all mappings from G to G which are 1 1 and on 2, which are 1 1 and on 2. So we now show that odd G is a subgroup of AG. For that, let two elements say T1, we take two elements T1 and T2. We take two elements T1, T of 2 in odd of G. Let we show that a T1 composition T2 is also in odd of G. Since each T1 T2 belongs to odd G, so they are both 1 1 on 2. Since T1 and T2 are 1 1 and on 2, so T1 composition T2 is also 1 1 and on 2. So next we show that T1 composition T2 is homomorphism. For that we take two point AB belongs to G. So this implies that T of T2 AB, this equal to T of 1, T2 of A, T2 of B. Since T2 belongs to odd of G, this implies that T1 of T2A and T1 of T2B, since T1 belongs to odd of G. So this equal to T1 composition T2A into T1 composition T2B. So T1 composition T2AB, this is equal to T1 composition A into T1 T2 composition B. So T1 composition T2 belongs to odd G. We write this 1. So next we show that for any T belongs to odd of G, to show T inverse is also in odd G. T inverse is also in odd G. So first of all, as T is both 1 1 and on 2, so this implies that T inverse from G to G exists, and this is both 1 1 and on 2. Let 2 point AB belongs to G. Then T inverse of A equal to let A1 and T inverse of B equal to B1. So this implies that A equal to T of A1 and B equal to T of B1. So this implies that AB equal to T of A1, T of B of 1. So this implies that T of A1 B1 যেহেতু T is a homomorphism. So this implies that T inverse of AB, this is equal to A1 B1, that is equal to T inverse of A and T inverse of B. So we take this 2. From 1 and 2 we say that odd of G is a subgroup of AG. So this implies that AG or G with respect to function composition forms a group with respect to function composition. So if we know that if G is a group and H is a subgroup of G, the necessary and sufficient condition is if we take two point from H, first property is A composition B is also in H for all AB belongs to H, and A inverse belongs to H for all A belongs to H. If these two conditions are satisfied, then we say that H is a subgroup of the group G. Here we take 2 point of odd G, that is T1 T2. In one we show that T1 composition T2 is also in odd G, and second, for any T in odd G, T inverse is also belongs to odd G. So odd of G is a subgroup of AG, and every subgroup is itself a group. So odd G is a group with respect to function composition. So next we show that in G, that is collection of all inner automorphisms of G, is also a group. For that we show that in of G is a subgroup of odd of G. So in of G is the collection of all inner automorphism, that is T of A belongs to G. We take two elements, say T8 TB belongs to in G. To show TA composition TB belongs to in of G. So let Y be an arbitrary element of the group G, then TA composition TB of Y, that is equal to T of A TBY equal to BY B inverse. T of A is equal to, by definition of TA, this is A of BY B inverse of A inverse. Now AB, we take this as Y B inverse A inverse is equal to AB whole inverse. So that is equal to T of ABY for any Y belongs to G. So this implies that T of A, T of B equal to TAB. This is belongs to in of G. We call this star. So next we show that if TA is an element of in G, then T of A inverse is also element of in of G. and TA composition TA inverse equal to T of A inverse. By star we get, by star what we get, T of AB equal to T of AB. Here T of A composition T of A star equal to T of A star, and A star means identity E, where T of E of X equal to Ex inverse, that is equal to X. So this implies that T of E is the identity mapping. So TA composition TA inverse, that is equal to I. So this implies that T of A, the inverse equal to TA inverse, this is belongs to in of G. Then from star and double star we say that in of G is a subgroup of or G, and every subgroup is itself a group. So in G is a group. Next we put that in G is not only subgroup of OR G, this is a normal subgroup of OR G. We show that in G is a normal subgroup of OR of G. For that, we use a necessary and sufficient condition of normality. That is, if G is a group and H is a subgroup of G, and we say H is a normal subgroup of G, if for any G of group and any H of H, we say that G inverse is also in H, then we say H is a normal subgroup of G. And H is normal subgroup of G. What is the necessary and sufficient condition? For all G of G and H of H, if we show that G inverse is also in H, then we say that H is a normal subgroup of G. Here we take any element of in G. Let T is a element of arbitrary element of OR G, and T of A is an arbitrary element of in G. So we show that TA composition T inverse is also in G. This by necessary and sufficient condition, the T of TA composition T inverse of X equal to T of T. By definition of TA we get A T inverse of X, A inverse. This implies that T of A, T of T inverse X, T of A inverse, as T is a belongs to OR G, so T is also homomorphism. So here we get T of A, T inverse, that is identity mapping. So I of X equal to X, and T of A inverse equal to T of A whole inverse, as T is automorphism. So this is equal to T of TA of X for any X belongs to the group G. So T composition TA T inverse equal to T of TA. So we get T composition TA composition T inverse equal to T of TA. So this element belongs to in of G. So by necessary and sufficient condition of normality, we can say that in of G is a normal subgroup of OR of G.